Hello, and welcome to today's webinar, MuSES EOIR Scene Simulation for AI and Machine Learning Applications webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenters today are Alex Klasius and Mark Klein. Alex is a thermal and CFD engineer in the Signature Modeling Group and has been involved in a variety of thermal and EOIR efforts during his tenure. Notably, he has aided in developing processes to create high-fidelity synthetic terrains using real-world inputs for scene simulation and investigated efficiency gains in synthetic EOIR video generation. He has been with Thermal Analytics for over 2 years and received a BS in Mechanical Engineering from Michigan Technological University. Mark is a senior engineer in the Thermal and Signature Modeling and Testing Group at Thermal Analytics. He produces and analyzes CFD, thermal, and EOIR signature models. At Thermal Analytics, he has developed and validated thermal and IR models of camouflage nets, humans, and military vehicles. He has been the lead engineer and project manager for several successful validations and field tests. Mr. Klein earned his BS degree in 2004, master's degree in 2007, in mechanical engineering from Michigan Technological University. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll be sending you the link following this presentation. And with that, Alex, if you're ready, you may begin.
Hi, I'm Alex Klasius, and I'm here with my colleague Mark Klein. Today I'd like to talk about MuSES electro-optical infrared scene simulation for artificial and machine learning applications. First, I'll give an introduction and motivation for using our tools for AI/ML applications. We'll introduce MuSES, our flagship EOIR package, go over process automation with CoTherm, and then Mark will share some results and lessons learned while using our tools to create synthetic infrared datasets. AI/ML has become a very popular area of research over the past few years and has proven to be very powerful for image analysis, including target detection and target recognition. However, these topics require large data sets to ensure that outputs are statistically significant. These large data sets are relatively easy to come by in the visible spectrum, but they are very hard to find large enough data sets in the infrared spectrum, going from the near infrared to the long wave infrared. And this can cause a problem and a bottleneck if you wish to use machine learning in that wavelength. So Thermal Analytics has a large model database to help with this limiting factor. Our capabilities and pre-made assets already include land targets, air targets, and sea targets, as well as human dismounts, which can be modeled outside of the visible waveband. Synthetic images of these pre-built assets can be easily generated on a very large scale with minimal human effort once a process is put in place. And to deal with the lack of data in this infrared wavelength and to create the synthetic images and data sets that we require, we utilize MuSES, our flagship EOIR software. MuSES is a thermal solver and infrared renderer, which takes inputs like 3D CAD geometry, part material thicknesses and thermal properties, as well as component heat sources, and a combination of boundary conditions such as environmental sources like the sun, the sky, and background around the target for radiation exchange, as well as air temperature and wind speed for convective heat transfer. The outputs from the combination of these boundary conditions and our inputs result in a physical temperature prediction and 2D sensor renderings, which can be generated for any waveband from the visible to the long wave infrared. MuSES is a complete thermal analysis tool, which means that all modes of heat transfer are accurately computed, including radiation between all parts of the model, convection, and conduction through the geometry. MuSES accounts for dual band radiation, so we're analyzing the shorter wave solar and the longer wave thermal infrared radiation independently, and we can incorporate environmental effects in our simulated models, such as sun position and sun strength throughout the day, cloud cover, and natural wind. When we want to model a target in MuSES, we start with a 3D CAD geometry with material descriptions and component heat sources to create a meshed target model, add some weather data, a mission profile, and GPS information to create a transient thermal solution, and then include sensor parameters, including waveband and atmospheric effects to create a radiance rendering. Contrast around the target, detection probability at range, and viewing angle are a couple different metrics that you can get from a series of these MuSES renderings. The finite element mesh that describes these models within MuSES, and the boundary condition setup is used to calculate a physical temperature prediction of the scene and the background. These physical temperature predictions are often the primary driver of radiance when looking through an infrared sensor. And MuSES then takes these radiance predictions for the background and target based on their physical temperatures, surface properties, and solar and sky reflections, as well as atmospheric effects to create synthetic renderings. And all of this can be done at different levels of sensor resolution and times throughout the day without needing to recalibrate any systems or waiting for your environmental conditions to be just right. Here are several more examples of images rendered within MuSES. You can investigate airborne targets such as jet fighters or helicopters with engine plumage, which also incorporates the heat emissions from those exhaust gases. You can look at a ground vehicle with a camouflage pattern and different optical properties on each of those paints within the camouflage. You could look at a commercial pickup truck with lunar glint coming off of the side window, or you could see that same behavior at sea when investigating a maritime model. Throughout thermal analytics' history, we have developed an extensive model database, which you can see some of here, including tracked and wheeled ground vehicles of different uses, airborne targets including jet aircraft, helicopters, and drones, maritime targets of different sizes, and personnel in numerous poses. The target model shown on the previous slide can be combined with a cluttered background scene. This top image shows a physical temperature prediction of what the scene would look like. We've included a soldier on the left-hand side and a Puma infantry fighting vehicle on the right-hand side. The lower images show a mid-wave infrared rendering of the scene. This type of scene and rendering can be used to train a target detection algorithm to pick out objects in the scene and a target recognition algorithm to classify those objects. Here in the red boxes, we can see the targets within the rendering, and these rendered images in MuSES automatically contain ground truth information, which can be used to label training data. There are many ways to model a background scene, such as the one that we saw on the previous slide. You could use a uniform and flat background with a more consistent radiance value. In the top left, you could add some 3D and explicitly modeled clutter like vegetation or bushes. You could use a more textured approach on the top right, which could include multiple types of building materials, different types of soil, asphalt, or any other type of ground cover. You can also insert MuSES target models into other simulation and training tools, or insert them into a previously measured infrared image, like in the bottom right. All of these scenes implement some level of clutter and complexity because background clutter is very important when it comes to target recognition algorithms or target detection algorithms. And that added complexity and clutter helps to train the algorithm to pick out targets correctly as opposed to parts of the background, such as a solar shadow or a bush or any other object in the scene which is not an actual target. One way to model these sorts of cluttered scenes is through an in-house process that Thermal Analytics has developed to take open source information, such as high-resolution satellite imagery and publicly available digital elevation maps, to create a more computationally efficient way to model multiple types of ground clutter. In the bottom right, you can see an example of what this sort of scene looks like. Those different colors in the bottom right represent different types of ground clutter. So that could be bushes or trees, gravel, dirt, sand, different road conditions. And further research is actively being done to expand the capabilities of this process. Here we can see a couple sample images using the background creation process from the previous slide. These images are in the mid-wave and long-wave infrared and were simulated at multiple points throughout the day. The differences in color that you can see throughout the background are due to a more computationally efficient way to model background clutter and variation, as opposed to including explicitly modeled vegetation and objects. As you've seen, there's a lot of information that goes into making a target and scene model, so we can automate some of this with CoTherm, which is a Thermal Analytics developed software. Inside of each of our models, we have a geometry of a target from our existing model database, some optical surface descriptions and terrain descriptions. These models are fed into MuSES with weather data and sensor parameters. And after some analysis, we can generate synthetic images, which can then be fed into an algorithm to give some sort of deep learning output. But if we want to manually vary all of these parameters that go into making the synthetic images, it's going to be very time intensive. So we can automate some of that with CoTherm and this data generation process. CoTherm is a tool developed by Thermal Analytics to aid in CAE code simulation, optimization, analysis, and automation. In this case, we're going to use it as an automation tool. Here's a quick example of such a process in CoTherm that we can use to iterate through numerous parameter combinations, including vehicle engine state, speed and heading, background type, weather conditions, date and time of day, and multiple sensor parameters such as waveband and resolution. And such a process like this can generate hundreds of thousands of images with little human input once all parameter combinations are analyzed. Here's a few targets. I can highlight that we have run through this CoTherm automated MuSES analysis. This process runs MuSES on these models and then goes through all the desired parameters to output a series of physical temperature predictions and synthetic radiance images, which you can see here. These images include differences in sensor azimuth and elevation angle, range from the sensor to the target, weather conditions, and levels of background clutter near the target, whether that includes a road or explicitly modeled vegetation. And when we take all these images and feed them into a target detection algorithm, it helps the algorithm get a better understanding of the 3D nature of our desired target. And now I'd like to turn it over to my colleague Mark to talk about some machine learning case studies.
All right. Hello, everyone. My name is Mark Klein. I'll be going through a couple of examples. A couple of machine learning examples that we've run at Thermal Analytics. So like Alex described, we can use MuSES and CoTherm to generate imagery of different targets over a wide range of conditions. So we can model, once again, we can model different targets with different sensor positions in different locations, with different weather conditions, different mission profiles, so changing vehicle operating states, vehicle off, idle, exercised, for example, and then we can model all these conditions with different sensors, different wave bands. So we can pretty easily change all these variables to generate pretty large image data sets. So a couple years ago, we did kind of an initial machine learning proof of concept. So as we all know, machine learning algorithms, convolutional neural networks have been successfully used for all kinds of image processing tasks, such as identifying faces, objects, and in all kinds of applications for self-driving cars. So we used a publicly available ResNet algorithm with a Python implementation using TensorFlow to kind of go through the process of training the network with MuSES generated imagery and then testing the output. So for this initial proof of concept, we used I guess, relatively small data set, 444 images of each of these three vehicles. So an 8-wheel troop carrier, a T-72 battle tank, and a Toyota commercial pickup truck. So pretty diverse targets, but kind of a simple or a nice, easy starting point. So we trained the algorithm using a set of images. These were all long wave infrared images. We used synthetic cluttered backgrounds like you can see in the images here. And we moved the sensor around the target with a couple different sensor elevations, a couple different sensor to target ranges, times of day, weather conditions, and then vehicle positions within the scene to get a little more variation in the background. So when we tested, so we trained that algorithm using the synthetic imagery, and then we tested it using a handful of different images. So these are three of the test images that we fed in to the trained ResNet. So you can see that these were all positive identifications. The image on the left is just a Toyota on a simple uniform background, so that's a synthetic image. The two images on the right are both composite images. So these are synthetic targets that were inserted into a measured background image. And the target was simulated under the same weather conditions as existed in the measured background image. So there's continuity there between the synthetic target and the background. But you can see these are all positive identifications. The percentages in this case are confidence numbers. So we saw generally fairly good performance with this initial test. So more recently, we've generated a larger data set, this time using 7 ground vehicles. And these 7 vehicles were chosen because they correspond to a publicly available measured data set. So for this work, we used a ResNet 50, a 50-layer ResNet with average pooling and the atom optimizer. Both the training data set and the test data set were were pre-processed by segmenting the target and normalizing via a per image pixel-wise z-scoring. So for this study, we are training the algorithm with MuSES synthetic data and then testing the algorithm with measured imagery. And this measured imagery comes from the DSIAC automatic target recognition training dataset. I'll probably say DSIAC for short. So this dataset is publicly available through DSIAC, and also the MuSES synthetic images were also augmented with a simple Gaussian blur to more closely match the DSIAC imagery. And then the targets in the training data set were randomly translated. So the DSIAC data set includes 10 vehicles. We simulated 7 of the 10. So the seven military vehicles shown here, we already had in our existing thermoanalytics model database. We didn't have an exact match for the commercial pickup or the commercial SUV, and the T-62 tank broke down during the test, so there wasn't much test data for that one. But we did model 7 of these military ground vehicles. This image just shows an example of the MuSES physical temperature prediction, just to highlight that these target models that we have quite a bit of internal detail. So we're accounting for all the significant heat sources within the vehicle, so the engine, the exhaust, and the cooling systems. So these images are shown with some transparency on the external surfaces, so that you can see into some of the internal engine details. So you can see the part of the engine blocks and the intake and exhaust manifolds and some of the exhaust components. So this slide shows a qualitative comparison between the MuSES predictions and the actual measured vehicles. So in the pictures there, the left-hand column is the MuSES renderings, and the right-hand column is the measured data for each. So this is for each of the 7 vehicles. These are all nighttime predictions, mid-wave infrared waveband, 1,000 meters from the sensor to the target. So these were all 7 of the models were, like I mentioned before, were already existing in the thermoanalytics database. In these models, so we updated the weather conditions to match the test data, but there wasn't much tuning done to get the models to match. We can see overall like decent qualitative comparison here. There are some differences between simulated and measured, but overall we were pretty happy with the initial agreement here between the modeled and measured. So in terms of generating a training image data set, so we simulated 2 different ranges, the 2 closer ranges from the DSIAC data set, 1,000 meters and 1,500 meters. We simulated day and nighttime conditions. We moved the sensor around the vehicle in 1.2 degree increments. I guess so the combination of all of the settings resulted in 7,200 images per vehicle. And this was done, we were trying to match the test data pretty closely here. And 7,200 is the number of individual frames in the measured. The measured data set is actually multiple movies or image sequences. So there's the total number of frames for each vehicle is about 7,200 for the 2 closer sensor ranges. The image here shows the background model, and then we modeled the vehicle at 6 different positions around that circle. So to generate this background geometry, we used the process that Alex described to combine Google Earth satellite imagery with a digital elevation map. And so we chose a location that was close to where the test was performed. And when they did the actual testing, they drove the vehicle around in a circle with a fixed camera position, and they actually watered that circle to keep the dust down during the test. So we simulated similar dirt conditions and moved the vehicle to 6 different positions around the circle. Within the MuSES model, we're not actually modeling the physical movement of the vehicle over the terrain. So we modeled 6 different positions to get a variation in kind of the local clutter around the vehicle, and also to get a variation in solar loading. So we generated 7,200 images per vehicle. The images were fairly small, 128 pixels square. The vehicle was centered in the rendered image chips. All right, so to generate the full data set, we used the CoTherm process that Alex described. So the CoTherm process takes care of the thermal calculation, the infrared renderings, and then also some image conversion that we need to get the output images into the right format for the algorithm training. So the total computational time with this process was about 2.5 days to generate 50,400 images. So that's 7 vehicles times 7,200 images each. And so this 2.5 days was done. This was spread over 2 computers, each with 16 processors, so 32 total processors. So we can generate tens of thousands of images per day, hundreds of thousands of images. Obviously this image generation time will depend on your specific model size and sensor settings. Here's some examples of the rendered images. The 2 on the left are daytime, the 2 on the right are nighttime. These are all mid-wave infrared, 1,000 meters from the sensor to the target. Just some sample outputs here. So we've got similar looking images that were generated for 7 different vehicle targets. So some results. So we started with 4 of the targets. So like I said before, we used a ResNet 50. We trained the algorithm with all synthetic data, and then we tested that algorithm with measured imagery. So the ResNet was trained with synthetic, tested with measured, and in this case, we're testing with all 7,200 images per vehicle. So you can see the overall accuracy here is 56%. So for example, the image here is a confusion matrix. So for example, if I feed in a test image of a BTR-70, 65% of the time that vehicle was correctly identified as a BTR-70. So if I average along the diagonal, I get 56% overall accuracy from the top left to the lower right. So if you feed in a T72, it's getting it correct 85% of the time. So if you add across the horizontal, the number should add up to 100%. So for the T72, 85% of the time it was correct. 5% of the time it was incorrectly identified as a BTR-70, for example. Here's similar results for all 7 targets. So once again, we're training with synthetic, testing with measured. With all 7, the overall accuracy drops to 40%. So for all 7, the random chance of getting it right would be about 14%. We're getting 40 here, so that's 2.8 times better than random chance. for the 4-vehicle case, it was actually 2.2 times better than random chance. So these percentages aren't great, and I can explain kind of reasons for these results. So once again, we're training with synthetic, testing with measured. The models aren't perfect, so there is some domain shift between the synthetic data and the measured data. Also, we're using all 7,200 frames from the measured image sequences, and these targets are automatically being segmented. In some cases, there's some target occlusion that we're not modeling, and the automatic segmentation that was done on the measured data wasn't perfect. So in some cases, we've got kind of partial vehicles, and the vehicles are hard to identify visually in some of the images. So these percentages aren't great, but we're testing with every single measured frame. Also, in this case, we're trying to teach to the test a bit by trying to match the measured conditions with our synthetic data. We're modeling the same times a day, the same sensor angles and positions, the same vehicle operating conditions. By trying to match that exactly, we may have tried to train our algorithm too narrowly. So we're actually working now on generating a broader synthetic data set that kind of is a little bit more diverse and kind of more broadly covers the measured conditions. So we're working on generating a larger data set with more variations of time of day, weather condition, sensor parameters, et cetera, to try to train the algorithm a little more generally. All right, so in conclusion, so MuSES offers a diverse set of tools to simulate a wide range of targets and levels of background fidelity. And when combined with CoTherm, it allows us to fairly efficiently generate pretty large image data sets that can be used for target detection and target recognition. And we show with some examples here that a neural network can be trained with synthetic IR images, and using synthetic data or using synthetic data combined with measured data can help to reduce the time and cost to train these machine learning algorithms. And that's the end.
All right, thanks, Mark. Thanks, Alex. I've got some questions coming in. Are there any best practices for target mesh resolution and or getting rid of internal meshes that would likely not contribute to heating?
Yeah, for sure. There are best practices. So we've developed some guidance for mesh resolution and how to make sure that your surfaces are properly connected to capture the right conduction paths. Either we can send you documentation, or we've got some mesh guidance documentation on our customer support site. So either I'd recommend logging into the customer support site to check out some of that, or send us a message through our customer support ticketing system, and we can help you with that.
All right, thank you. Can you provide more detail on the terrain creation process with satellite imagery?
Yeah, so that's a proprietary process that we've been developing. It takes in Google Earth, satellite imagery, and digital elevation map data, and we've got it uses C++ code to combine the satellite imagery with the digital elevation map data to automatically create a meshed surface that's been parted out by the different types of ground cover. So we take the satellite image and we index the colors to get a certain number of discrete background types, and then we've got some code that automatically separates that into different parts that can be imported into MuSES. So currently it's only available for us to use internally. If you've got specific backgrounds that you would like to create, we can provide that as a service.
All right, thank you. Any comparisons done on the ResNet 50 performance that was trained with A, measured data, or B, a combination of measured and synthetic data?
We've done a little bit of testing there. We plan to do more with combination of synthetic and measured. I guess for reference, we saw before we started training with synthetic and testing with measured, we trained the algorithm and tested with both synthetic and saw very good performance. So when we trained with synthetic and then also tested with synthetic, we saw better than 95% accuracy. And we also trained and tested with measured and also saw quite high accuracy. And we will be experimenting with combinations. And like I said, we're also working on generating a larger synthetic data set.
Okay, thank you. I didn't think MuSES had capability over the visibility band, but I saw reference in the presentation to the visible band. Does MuSES actually have predictive capability in the visibility band?
Yeah, so MuSES can render in the visible band, but it's only it's a radiance image or like a grayscale prediction. We don't do a true color visible prediction. So we can predict radiance in the visible band, but we don't do a true color image prediction.
Thank you. Is terrain thermal or still visible after you processed?
When we create we do a full thermal prediction on the background on the terrain. So the process that we described is a way of taking the visible imagery and basically using that to create a surface mesh that's parted out for different types of ground clutter. And then once we have those different types of ground clutter separated into different parts in the mesh, then when we do the thermal solution, we can predict the physical temperatures for those different types of ground cover, like dirt, gravel, asphalt, concrete, grass, trees. So there's built-in background models within MuSES for those different types of ground cover.
All right, thank you. Is the CoTherm rendering process available to customers?
We've released it to a small number of customers for testing so far. We're working on making some improvements to make that more user friendly. So I think at some point it'll probably be included with the examples that are distributed with CoTherm, but currently it's available upon request, and like I said, we're working on making it a little bit more user friendly so that we can more widely distribute it.
Okay, well, it looks like that does it for questions. So that will complete today's webinar. Thank you everyone for attending and also for your questions. Everyone will receive a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. Again, thanks Mark, thanks Alex, and everyone have a nice day.
Thanks everyone.